Okay, let's talk about normal distribution. We learned about the empirical rule, right? Okay, what does that tell us? That tells us that I'm not working here. There's a problem here. Okay, that's on. Yep, they should talk to each other. Connected. Okay, I think we're connected now. Good. Bingo. Okay. So what we learned about the normal distribution? We learned that there are many things in nature that are determined by chance. So for instance, if we have a population that has a certain average weight, certain average blood pressure, and so on and so forth, when we sample, when we randomly pick a person from that population, we might pick a person that's exactly in the middle, that's exactly the mean of that population. But the probability of that occurring, imagine if the average weight in the among all Hunter graduate students is 152 pounds, and I randomly pick someone from all Hunter students, what would be the odds that I would pick somebody that's exactly 152 pounds? Probably be very rare, right? Even though it's probably the most frequent weight, or very close to the most frequent weight. Okay. However, if you look at it from another perspective, what's the probability that I would pick someone from the Hunter population that's less than 152 pounds or more than 152 pounds, the average? Well, it's equal, right? Just as likely I would pick somebody lower as somebody higher, right? Well, what's the probability I would pick somebody that's 150 pounds or 154 pounds? Well, that's pretty likely because it's pretty close to the average. But as I get further and further away from the average, it's less and less likely that the random person I would pick would be that weight. What's the probability I would pick someone that's 225 pounds? Well, that's so far from 152 that there are probably not that many people that are that weight, and the probability of me picking them is not that high. Similarly, if I go the other direction with a lower weight, it's going to happen the same way. So if I were to take repeated samples from this population, or even just look at the entire population, it's very likely that the distribution of the weights in this population, just because of chance, are going to look something like this. Oops. It's not agreeing with me here. Let me try this again. Oops, still not agreeing with me. Okay, here we go. Probably looks something like this, where the average weight would be right in the middle, say 150 pounds. I'm going to call it 150, just to round things off a little bit. So this can represent two things. It can actually represent the entire population and the height. Just you can imagine this like many, many small histograms. The height represents the number of people at that weight. Or you can also look at it as looking at the probability that I would pick someone that's at that weight. Now we know, because of the nature of random normal distributions, that this shape has a certain property to it. We know that the two principal things that we deal with here are going to be the mean and the standard deviation of this population. We know we've calculated that before, and we know what those numbers represent. One represents where the middle is. The other represents how spread out it is. The reason why we're so interested in the standard deviation, why we make such a big fuss about that particular odd kind of calculated statistic, the reason why we're so interested in that is because it has a special property where this distribution is concerned. And that is, according to the empirical rule, that if we go one standard deviation below the mean in normal distribution and one standard deviation above the mean, that's 68% of that population is going to be between those two numbers. Okay, so if my mean is 150 and my standard deviation is 10, well then what's that range going to be? That's going to be from 140 pounds to 160 pounds. Okay, everybody comfortable with that so far? Okay, I'm beating this to death, I know, because there's a reason for this. Because what we're doing tonight is so fundamental to what we're going to be doing for the rest of the semester in terms of sampling and making comparisons and t-tests and confidence intervals and all kinds of other stuff like that. So that's one thing we know about the empirical rule, about standard normal distribution. The next thing that we know is that if I go 2 standard deviations below the mean and 2 standard deviations above the mean, anybody remember what percentage that represents? 95%. Right, exactly. And if I go to 3 standard deviations above and below, it's 99.7%. But there's a lot that we can derive from this as well. So for instance, I know that, I know that if I'm going to look for the portion of the population that is between the mean and 1 standard deviation above the mean, what percentage is that going to be? Well, if it's 68%, it's going to be 34%, right? Roughly 34%. We know that because the normal distribution, in addition to having these properties, is symmetrical. So you know the area below is the same as the area above. If I were to ask you and I'm going to write in here now that the 2 standard deviations below is going to be 130, and a 2 standard deviation above is going to be 170. If I were to ask you what proportion of the population was between 160 and 170, well, let's say above 160, right? Well, above 160, you'd say, well, this is 50%. This was 34%, so that leaves 16% in here, doesn't it? Right? Okay, let's take this a little further. What percentage is above 170? Right? Well, the percentage above 170, if this is 95, that's going to be 2.5% in there. So we can do all sorts of calculations using this empirical formula, right? In trying to understand what the probabilities are of selecting people or what proportions of the population are within these ranges. Now, of course, we're going to get into a situation where, for instance, if I wanted to know what percentage of the population was below 135, well, 135 is, I'm going to write a formula on here. Z is equal to x minus mu over standard deviation over sigma. Okay, well, Z represents the z-score, which is another way of saying number of standard deviations, right? So 135, you can see this intuitively. 135 minus 150 is over 10, standard deviation of 10. That's 1.5, right? Well, the empirical rule, we only know that for whole numbers of standard deviations, right? So if I'm over here at 135, I want to know what this area below 135 is, what percentage of the population is below 135. I can't really get it from the empirical rule, right? I have to go to some other tool. And that other tool is either going to be a table, or it's going to be something calculator or something online or SPSS and so on and so forth. I'm going to use a table. On Blackboard also, I'm pretty sure I uploaded the Z table. Okay, so you guys remember this, right? I've discussed it with you in the air, in the cloud, so to speak, right? Because I've been out for a while, and we had a test last week. I missed the week, and we had a test last week. But I know that you guys have seen this, right, in videos and Professor Wyke and some videos and stuff like that. So how are we going to use this Z table? Well, this particular Z table. And I'm not sure if you guys used this the last time. I prefer this one. It's on Blackboard. And I prefer it because it has the negative and the positive numbers. It's 2 pages. You don't have to do as much interpretation. Well, what does this mean? This means I can look up the area that's associated with a z-score of negative 1.5, right? That 100, which represents 135 pounds. Okay, well, how do I use this? I go to the Z table, and there's a whole array of numbers here, 10 rows of numbers, and a column that says Z at the top, and then a column, and then a row goes across the top that says 0.00, 0.01, 0.02, and so on and so forth. Those are the third digits of your Z-score. So our Z-score is 1.50. So I would go down, since it's a negative number, remember, because 135 minus 150. It's negative 1.50. So negative 1.50 is here. negative 1.50. Now, had it been, and the first column is a 0. So that's my third digit in the 1.50. So had it been 1.58, I would have gone down to negative 1.5 and then gone across to 0, 1, 2, 3, 4, 5, 6, 7, 8 to get the area that I'm interested in. But I happen to be lucky, it's 1.5, so it's just this area right here. So it's 0.0668. I'm going to go back up to the top here. What does that represent? If you look at the diagram that's at the top of 99% of these z-tables, it gives you clues on how to interpret that area. In the case of this table, anything that you look up down here represents the area to the left of the z-score. So if I were to ask you, what's the probability of selecting someone from this population that has a weight under 135, you would say, I got to move it up. Yeah, you would say 6.0, negative 1.5. 6.68% or 0.0668 if we were expressing it as a proportion. Okay? So if we were a number that was greater than 100, let's try this again for 100 and let's say for a number like, let's say 162. Okay, so that's going to be over here. Oops. Oh, I'm using an eraser. Okay, so let's say it's 162. So what's the z-score for 162? It's going to be equal to 162 minus 150 over 10 is going to be equal to 1.2. Okay, that's a positive 1.2. Now, if I go back to my table, okay, if I scroll up here, these are all negative numbers. When I get to 50%, the z-score is 0. It's the mean, so the z-score is 0. Okay, if I go further down, okay, let's see where I get 1.2. 1.2 is here. All right, so 1.20, again, had it been another digit there, I would have moved over, is 88, I'm going to call it 88.5%. So what does that tell me? That tells me that 88% of the population is below 162 pounds, right? Leaving 12% of the population above 162 pounds. Well, I could actually say to myself, well, if this is 88% of the population that's 162 pounds, and that's 88% from there down, and it's 6% from 135 down, I could say between 135 and 162, we have 88 minus 6, about 82% of the population. I've rounded the numbers there to make it a little easier. So there's a lot of things that we can do to understand this distribution, manipulate these numbers so they work for us. Okay, well, this is great because this is what we understand about the normal distribution. Okay, and we'll maybe go through a problem or two also. Tonight, though, we're going to take a look at another property of samples and normal distributions. Okay, and the way that's going to work is going to be a bit different. Okay, we're going to do an exercise now that's on here. Okay, this opening exercise. Okay, now this, what we have here, I have an Excel version of this. And let me see if I can't find it. If I have to, I think I can actually, nope, it's a picture. You see it's on Blackboard. Let's see. Yep, there you go. Good. I'm glad you noticed it. The screen's so tiny. Open. Okay. This is the same table as you're looking at on your piece of paper there. I'm going to call this my population. Right? Population could have 100 people, could have 1 million people, could be a country, could be the entire world. Right? This is my entire population. So I'm going to find the mean, sigma, right? Mu rather, right? When we describe the population numbers, parameters, we call them parameters instead of statistics. when we're describing the population parameters, we describe them with Greek letters. Mu is mean and sigma is standard deviation. So I'm going to find mu for this population. It's basically the arithmetic average. Okay, and I'm going to find the average of all of these 100 numbers. Okay, and the average is about 50. It's actually a little bit less, I think. I've got this rounded off, 50.1. Okay, now I'm gonna find the sigma. I'm going to abbreviate it with that for the time being. Okay, and that's going to be equal to the standard deviation of the entire population. Okay, the standard deviation of the entire population is about 9. So the mean is about 50. The standard deviation is about 9. So now, think of all the stuff I know about this already. I already know that 95% of these numbers, if it's a true normal distribution, are going to be between 50 minus 18, right, 2 standard deviations below, and 50 plus 18, 2 standard deviations above, and so on and so forth, all the other things that we know from the table. Okay, so now I'm going to do something a little bit different. When we work in biostatistics, we never know the population mean or standard deviation. It's very rare for us to know that. The only time we know it is when we take a census, when we sample everybody in the population. Doesn't matter how big a sample you take. If you don't sample everybody in the population, you never really know what the mean is. And when we do these studies, we're always trying to estimate what the mean is of this population, what the mean is of this population, how they compare. Are they really different, right? The irony of the whole thing is we never really know for sure, right? We only know to a certain level of certainty. And the statistics that we're going to work with is going to help us understand what that level of certainty is, which is important. So that we know that how uncertain we are is as important as how certain we are. We know what our level of uncertainty is as well. Okay, so now we're going to do something now, and we're going to actually do a sample from this population. So what I'm going to ask you to do is I'm going to ask you to randomly sample yourselves, right, on paper, randomly sample 9 people from this population, 9 numbers. This one, this one, this one, so on and so forth. The only problem is if you do it this way, if you're right-handed, if you're left-handed, you're going to bias your sample. So we need a mechanism for having a true random sample. I put another file on Blackboard. If I can find it in the background here. Let's see if I can do it this way. Do I have it open? Doesn't look like I have it open. Okay. I'll just re-download it. Let's see, random number table. Okay, I'm going to open my version of it up. It's called random number table. You guys will have it there on your. Okay, this is what it looks like. This is a publication. They have entire books printed like this. They're random digits. There's actually, believe it or not, nowadays you probably would not use this to generate random numbers unless you're trying to do it with the power out. Right. So, but this is how we used to do it a while ago. However, it's still a valid way to do it. There are entire, literally volumes of publications that have random digits. There's actually specific instructions on how to use this. But in general, the way people use this is they start from a random location. Like I'll start at the top of this page. I probably shouldn't start at the top of a page, but I'll start at the top of a page. Right. So I'll start at the top of a page. And I'm going to use this so that these two numbers, 4 and 0, they represent the row and the column of the number that I'm selecting, right? So 4 and 0, if I go to my table, row 4, column 0 is a 65. And then I would go back to that table and I would say next one's 60. So that's row 6, column 0. Row 6, column 0 is a 42. Then I would go back to that table and the next one's going to be, now I can stretch across the column here, 3, 1. Row 3, column 1, 49. So I'm going to ask you guys to do that. Okay. So as soon as I get like about maybe 10 or 15 of you guys, throw up a number at me, then we're going to do something. We're going to take a look at that. Okay. So work. I don't want to kill too much time on this. So I'm going to go back to Excel. 9. Take 9 random numbers, find the average of those random numbers. That's it. No standard deviation, no nothing. I just want the average of those numbers. By the way, I can put up a bunch of links to websites, other kinds of sources that you can use, functions you can use in SPSS, Excel to generate random numbers. Okay, this is a pretty primitive way to do it, but people still do it this way. Old people, but people. Okay, I'm going to open up Excel again so that we can collect all this information. Okay, good. Okay, so as you do it, anybody that's completed, as you complete it, just yell up a number to me. One number, the average for the 9 numbers. Up 52? 62. 43, you can round it off. 2 digits, good enough. 52. 50? 58? Okie doke.
48.
Need a few more. Okay. So you guys have taken your first random samples. You started a career in statistics and probability.
53.
I'm sorry?
53.
Okay, let's stop there. I don't want to kill all night on this, right? Okay, so I'm going to take the average and the standard deviation of these 2 numbers. And the standard deviation. Okay, what do you think about the average? What's the average likely to be? Yeah, probably be around 50, right? You'd expect the average of these repeated samples of size 9 to be similar to the average for the general population, right? Let's do that. Okay, average. The mean of the samples now is about 51. Not bad, pretty close, right? Now, almost the same as we got before with the whole population. How about standard deviation? What do you expect the standard deviation to be? Smaller, larger, or the same as the standard deviation for the population, which was 9? Larger? Larger? Everybody agree larger? Why do you think it'd be larger? Let's think about that for a second. The standard deviation is the measurement of the spread. These numbers are a lot closer together than the numbers in the population, right? Why are they closer together? Because instead of just grabbing 100 people or a whole bunch of random people, now you're taking 9 people, averaging them, so they come out closer to the mean. So the spread here is going to be narrower. Let's see what it's going to be. Oh, it's 6. What was it before? 9. Mathematically, if we had done more people, if we had done a bigger sample, and so on and so forth, theoretically, what we should have seen is that the average should approximate the mean of the sample, of the population. And the standard deviation should be approximately equal to the standard deviation of the population divided by the square root of the sample size. Right? Whoops. I should have put a little space in there so it didn't use that equal sign. Standard deviation is equal to the standard deviation of population. So we really should have, if we kept done it off and done enough samples, it would have come up to be what was it? 9 divided by 3, the square root of 9. The sample size 9. 9 divided by 3 would be 3. So our expectation is that if we did it enough times, theoretically, if I sampled thousands of times from the same group of numbers, population, the standard deviation would wind up being 3. Okay, that's important. Why is that important? Because now we know that if we have a population, we know if we take a sample, that our sample is going to approximate the mean of that population. Maybe not exactly, but it's going to approximate the mean of that sample. The bigger the sample is, the better it's going to approximate the mean. And that if I were to take samples over and over again, the variability, the standard deviation of my samples would be the standard deviation of the population divided by the square root of the sample size. I have an understanding of how likely my sample is going to approximate the mean and the standard deviation of the population. Okay, that's important. So now we understand more about how samples work. Okay, so let's move on to some exercises. And we're gonna has the word I didn't notice it tonight. Has the word confidence interval come up in the lecture yet? Not yet. Okay, good. We'll try and avoid that word then. I'm sorry I mentioned it now. Okay, let me find my Word document here, and let's give this a try. Okay, if the total cholesterol value, this is just a normal, because first of all, let's read it and interpret it. If the total cholesterol values for a certain population are approximately normal and distributed with a mean of 200 milligrams per 100 deciliters and a standard deviation of 20 milligrams per 100 deciliters, find the probability that an individual picked at random from this population would have a serum cholesterol between 180 and 220. Okay, anybody say anything about a sample there? They're talking about the population here. So this is going to be either the Z table or the empirical rule, right? So between 180 and 220, the mean is 200, right? I'll make that bold. The standard deviation is 20. They've given us the mean and the standard deviation, right, for the population. So, gee, 200, 180, 220. Yeah, one standard deviation. So the probability that you would randomly pick someone, 68%. Everybody agree on that? Good. Yes? In the back there? Yes. Okay. Between 160 and 240. 95%, right? 2 standard deviations in either direction. How about greater than 225 milligrams per, right? Well, 225 now, can't use the empirical rule. So I have to pull out the big guns. I have to go to my table, right? So what's that going to be? I'm going to see if I can't sketch this.
Why can't we just do more than this in exome?
You can, absolutely. It does the same thing, yes. Right. Absolutely, you can.
Because it's cumulative probability up to 225,
right? Yes. No, well, norm dis does the same thing our table does. It gives you the area to the left, right, of that value. So let's do it both. I'll tell you what, let's do it both ways. So what is the z-score for 225, right? The mean's 200. 225 minus 200 is 25, divided over the standard deviation, which is 20. So what is that? That's, I lost track. But 225 divided by 20 is 1 1/4, 1.25, correct? Am I right about that? Z-score is 1.25?
Yeah.
Okay.
1.125.
1 point.
What do you want divided?
It's 225, right?
225 divided by 20.
220, well, hang on. 225 minus 200 is 25.
Yeah.
Divided by 20. That's 2 1/4. It was 1 1/4, right? 1.25. Okay, we're in agreement on that. It's 1.25, 1 1/4. Okay, so let's use our table to find that. We'll use Excel as well. There's our table. So 1.25 So actually, this time we have to use that third digit, right? 1.2, 1.20, 1, 2, 3, 4, 5. It's like 89, almost 89 and a half, right? So 89.5% of this population is below that z-score and below that. Remember, it measures the area to the left. Is below that. So if the question is what percentage of the population is above that, and we got 88, it's going to be 10.5%. Okay, everybody comfortable with that? Let's try that in Excel. Okay, equals norm s dist parentheses, and it asks me for the z-score, which is 1.25, and it's going to give me a proportion. Whoops, doesn't like my parentheses there. Oops, and I have to expand it to get it to display right. Right, 89.5%. So if I want to know the area, that's the area below. If I want to know the area above, I got to subtract it from 1. Right, so 10.5% roughly, 10.6%. Okay, what's the next question? Next question asks, less than 150 milligrams. Less than 150 milligrams, so that's 50 below 200, right? Divided by the standard deviation of 20, that's going to be 2.5. Okay, everybody agree? 2.5 standard deviations. So I go back to my table. 2.5 standard deviations is going to be 0.0062, about 0.6%. What percentage of people what's likely to pick a person that's under that value? It's going to be about 0.6%, 0.006. Okay. How about between 190 and 210? That's half a standard deviation below. In other words, negative 0.5 standard deviations and half a standard deviation above. And you're looking for the area in between. Well, how might you figure that out? Well, if you start with the z-score plus 0.5 plus 1/2 standard deviation, find that area. Okay, and I'm going to draw this here. If I were to say let's find the z-score for a z-score of plus 0.5, that was, what did I say was 210? And 190, which is 10 below divided by 20 is negative 0.5, right? Well, if I want the area between these two, I could just find the area below this for plus 0.5, and then the area below negative 0.5, and just subtract one from the other, and it leaves me with the area in between. Okay, so let's give that a try. Okay, so negative 0.5 is going to be about 31%. I'm rounding this off to keep this quick. And positive 0.5 is going to be about 69%. So 69% minus 31% is going to be 69, 31, 37% between those two. Okay, so you can use this, you can manipulate to do this all kinds of ways. Okay, so let's move on from this. Let's now apply the central limit theorem to this. Okay, here's a good public health example. You have 100 bottles of detergent and find that on the average, each bottle will be sufficient for 57 loads. You know that the standard deviation for the entire production of 100,000 bottles is 5 loads per bottle. Okay, you know the standard deviation, how many loads you can get out of a bottle. So what does that mean? That means on the average, most bottles will give you 57 washing loads. But, you know, some give you 52, some give you 65. But the standard deviation for the entire production line, all you've made is 5. What's artificial here? What's artificial here is we would probably never know what the standard deviation is, right? So it's kind of artificial to actually say we know that. Right now, this is just a crutch for us so that we can use what we know about sampling distributions in order to do this calculation. Okay, so is 57 mu or x bar? Okay, you sample 100 bottles, you get an average of 57 washing loads. Is that mu or is it x bar? Hang on a second. Is it the population mean or is it the mean of the 100 bottles we sampled? It's the mean of the 100 bottles we sampled. That's x bar. Right? We're going to call that x bar. Okay, what is 5 sigma or the standard deviation? Is it the population standard deviation or the sample standard deviation? It's the population, and that's a construct. You know, we've been told that in the example. Normally, we wouldn't know that. In fact, normally, if we took a sample of 100, we'd be forced to use the standard deviation of the sample we took to approximate the population standard deviation. But then it makes things a little confusing with our rule. Okay, so let's now, one of the things I've neglected to tell you when we looked at this is when we did that example where the mean was 150 and the standard deviation was 9, and then I said, oh, you know, if we take repeated samples of size 9, well, now what we should find is that our new distribution of many, many samples of size 9, our new distribution of all those new means, is going to have an average close to approximating the population, 50, but it's going to have a standard deviation which is going to be smaller, which is going to be equal to the population standard deviation divided by the square root of the sample size. In other words, 3. Well, to keep things from being confused, if it's possible to do that, what we're going to do is give the sample standard deviation a new name. Instead of calling it standard deviation, we're going to call it the standard error. Okay, but you understand all it is standard deviation, all these repeated samples. So we're going to call that the standard error. Okay, so let's go back here. So calculate standard error for repeated samples from this population, okay, of size 100. Okay, so if we told you that the standard deviation for the entire population is 5, what would you say is the standard deviation for repeated samples? The standard error, in other words. Well, what is it? It's sigma, which is 5, divided by the square root of the sample size, which is 100, right? So it's, let's see, 5 divided by the square root of 100, which is 10, is 1/2. The standard deviation is 1/2. Standard error is 1/2. Okay, so okay, now, you know, I hate to go ahead and do this to you guys, but maybe we'll actually go ahead. Maybe we'll get a little bit ahead of this the lecture tonight. How's that sound? Okay, so now what does that tell us about this whole thing? This tells us that if we take many repeated samples and we know the population standard deviation, we should have a pretty good idea of where all these samples are going to wind up, right? So we can say to ourselves, well, if I take all of these repeated samples, I want to close this and reopen it so I can get a fresh page to work with here. Get to the desktop. Okay. If the true population mean is here, and we know that the population and the mean, the standard deviation of the population is 20, as we do in this case. Sigma, in other words, is 20. And we're going to take repeated samples of size 100. Right? Well, we then know that if we, instead of having this the population distribution, we make this the sample distribution, right? I'm going to call this X bar now instead. Well, X bar is going to, because it's a nice big sample, 100, X bar is going to approximate, it's not going to be same, but it's going to approximate the mean, okay? So I'm going to say to myself, well, gee, how, if I took the samples of size 100 over and over again, how would that relate to this X bar? Well, okay, let's take a look at this. So X bar, the standard error, is going to be equal to, my new standard deviation is going to be equal to sigma divided by the square root of the sample size, which is 20 over 10, which is equal to, excuse me, did I say that? Oh, it was 5. It was 5, right? 5 over 10, which is 0.5 or 1/2, right? Well, gee, well, what do I have here? What I have here is I have a situation where now the standard error, the standard deviation of these repeated samples is equal to 0.5. Well, that, if I look at this and you apply the empirical rule, I could probably make an assumption that 95% of my samples, if I take sample size of 100, are going to be between 2 standard deviations below what I'm estimating the mean to be, and 2 standard deviations above where I'm estimating the mean to be. So that's going to be equal to, let me see, that's going to be equal to, let's see, that means that it's going to be between this number and this number 95% of the time. So I can actually say to myself, gee, if I take X bar and I subtract 2 times the standard error from X bar, and I take X bar again and I add 2 times the standard error, I would be right 95% of the time in saying that I would expect to get a sample result for a sample size 100 within that range, right? So what would that be? That would be what was X bar again? It was 57. That would be 57 minus 2 times 0.5 is 1. That's minus 1 is equal to 56. And 57 plus 1, 2 times 1, 2 times 1/2 is 1, is 58. So 95% of the time, I would expect to get samples between 56, and 58. Well, the only problem is we don't really know that X bar is really the mean of the population. We're just guessing at that. But we're going to use this a slightly different way. We're going to say to ourselves, well, yeah, but it's the same idea that if we knew what X was, we could use the standard error to predict, how likely it was we get a standard deviation between a mean in a sample of 100 that was within 2 standard deviations of the real population. We're going to use it a little bit differently. We're going to call this a confidence interval. And what that's going to represent is, in this situation, we are 95% confident that the true population mean is between 56 and 58. And we're going to call that a confidence interval. So whenever we take a sample, right, if we were to go out right now and do a survey, and we're going to survey a certain population at a nursing home or something like that and check their blood sugars or something like that, and we found that the randomly sampled maybe many nursing homes around New York City. And we want to know what the average blood sugar is for elderly patients in nursing homes. In New York City, we don't have the resources to sample every patient in every facility, so we randomly select facilities and patients and so on and so forth. We get maybe 100 patients, and we find the average. We use the average. We guess, and we say that the average, the standard deviation for the sample we got, is also known. Or maybe somebody did a bigger study that calculated the standard deviation. So we know the population standard deviation. We don't know the mean, right? So we say to ourselves, okay, well, how does that help us? What it helps you know is when you get your answer back, you take your sample of 100 people, you find the average is 110. Well, without using the central limit theorem, you only know that the average for your sample was 110. And you're guessing that the population mean is similar to that. But now if you estimate or guess at this, if you know the standard deviation of the population, and there's ways we're going to figure that out. If you know the standard deviation of the population, now you can calculate, because of the sample size, what the standard error for your sample size would be. So now you know the standard error, now you can calculate a confidence interval. So not only that you know that the mean level, the mean sugar level is 100, whatever the units are, per deciliter, micrograms or milligrams or whatever. You know that the mean is 110, let's say. Now you also know that even if it isn't 110 for sure, you know at least that you're 95% certain that it's, say, between 106 and 112. Get it? Get what we're driving at here? Knowing that confidence intervals allows us to know not only what our sample mean is, but how certain it is, or what range within we can have a known level of confidence that the true population mean lies. Okay? That's a lot more valuable than just having one number and just having no idea how accurate it could be. Now we have that number, but we also have a good handle on how likely it is that we're going to be close to the population mean. Yes?
Would you be using 2 or 1.96?
Oh, okay. Now, I've been lying along. I've been lying like a rug this whole afternoon, right? You guys, most of you guys realize I've been lying. The reason why did I use 2? I used 2 because the empirical rule tells us that 95% of the sample outcomes the population means are between any normal distribution are between 2 standard deviations of the mean below and above. In reality, that would suggest that a z-score of -2 has an area to the left of it of 2.5%, and an area and a z-score of +2 has an area to the right of it of 2.5%, because we're talking about the middle 97.5%, right? 95%. In fact, let's go to our table and see what that really is. A z-score of -2, really represents an area of 2 and about 1/4%, 0.0228. It's not 2 1/4, right? So it's just an estimate. That empirical rule is just an estimate. What number really represents, what z-score really represents 2.5% to the left of that number. So let's go across here. 2.5, okay, 57, 50. So it's right around these two numbers here, right? This column and this column. So that's 7 and 8. Most people choose 8. 8 actually is a tiny bit closer when you round it off. So the real number, real z-score that represents 95% of population and 95% of the population is 2.58. I'm doing this wrong. Hang on a second. 1.9. Hang on. 2.0. I got ahead of myself again. -2.0, 2.28. I want 2.5. So I'm really got to go lower, right? So it's going to be down here. Here's 2.025. Here's 2.25% right there, and it's represented by 1.96, right? So the real z-score for 95% on either side is going to be a z-score of -1.6 to a z-score of +1.6. If you're looking at it more accurately than just using the empirical rule. How about 99%? Right? Well, 99%, right? What's 99% going to be? That means 0.5% is going to be above and 0.5% is going to be below. So we could say that if we want 99%, let's look for 1/2%. 0.005. Okay, we're about here, and that number is 0.258. Right? 2.5 and then 8. That represents 0.5% below, 0.5% above. So that z-score represents 99% of the population with 0.5% below and 0.5% above. How about 90%? 90% would be 5% below and 5% above. So where is 5% here? 5% here is 5% here is about 1.6, and the closest one looks like 4. 1.64 standard deviations below, 1.46 standard deviations above represents the middle 90%. Why am I even bringing that up? Well, for one is that you caught me using the rounded number, you caught me using the empirical rule, but in addition to that, to calculate my confidence interval, instead of using 2, I should have used 1.96. Subtract that and add 1.96 times the standard error. And that would represent a 95% confidence interval. Now, if I had used instead 1.64, minus 1.64 and plus 1.64 times the standard error, what would my confidence interval be there? That would be my 90% confidence interval. I would be 90% positive that I would have captured the mean. Right? Okay, well, how about if I were to say 99%, 2.58? You would use 2.58 here, subtract 2.58 times standard error, and add 2.58 times the standard error. Okay, so that would be a 99% confidence interval. Now, let me ask you a puzzle. Let me get this out of the way. Get a fresh sheet again. Okay. Okay. That's for a couple hours there. What do you think is going to be wider? The 95% confidence interval or the 99% confidence interval? You guys are intuitive. I know, but most students tell me the opposite. Why is it going to be wider? It's got to be wider because it's more certain that if you're 95% confident, you can afford to make the range narrower because you don't have to have as much confidence that you capture the real mean. If you say if you want to be 99% sure, you got to make the range wider in order to make sure that you capture the mean 95% certainty. And if I say 90%, that's really narrow. That can be quite a bit narrower because you're not demanding to be as certain that you capture the mean. Mathematically, you sensed it mathematically, because mathematically, if you look at this, for 95% confidence interval, right, you would use x bar plus or minus 1.96 times the standard error. For a 90% confidence interval, you'd say x bar plus or minus 1.64 times the standard error. And for 99%, you would say x bar plus or minus 2.58 times the standard error. So which of these is the widest? Well, you're multiplying the standard error by the biggest number for the 99% confidence interval. So you're going to be subtracting and adding the biggest number, which is going to make it the biggest range. So this is the widest of them. And it has to be wide because you want a lot of confidence that you really capture the true population mean. We never know the true population mean, but now we got a mechanism for estimating how likely it is that what we found in our sample represents the population mean. So if I'm 95% confident, I'm 95% confident that I have really captured the population mean. If I take a sample 20 times, how many times will I actually capture the sample in a perfect world? How many times will I get the population mean within that range, and how many times will I miss it if I'm 95% certain? 19 times I would capture it, and one time I would be wrong. The population mean would be outside of my estimate. 99%, 99 out of 100 times I would capture it, and one time out of 100. In a perfect world, again, your results are going to depend on chance and stuff like that, and that can do a lot of weird things, right? So this is why we're so interested in this idea of a central limit theorem. How am I doing on time, by the way? 7:12. We're doing good on time. Okay. All right. So this is why we're so interested in this idea of the sample. Okay. We call this, what do we call this whole set of rules here? We called it the central limit theorem. There's another interesting thing that the central limit theorem does for us. And that is that if we start out with a population that is not normally distributed, maybe it looks something like that, right? Really weird. It's got a mean over here, right? The median is a little bit further away from that and stuff like that. If I take repeated samples from that non-normally distributed population and I plot the sample means, right? Well, for one thing I know for sure is it's going to be narrower because just the fact that I'm taking a sample and and plotting these and finding the average of all the samples, it's going to be a narrower distribution. The other thing about it is it's going to be more normal than the original one is. Because even though it's so funky, half the numbers are going to be below the mean, half the numbers are going to be above the mean, and you're going to randomly be choosing them. The larger the sample size is, the closer to a normal distribution that your sample distribution comes. So the central limit theorem tells you basically, if you have a large enough sample size, you can ignore the fact that your population is not perfectly normally distributed, apply all these great rules to it that involve the mean and the standard deviation. So look at all the stuff we're getting from this. We're getting ways to measure the mean, the samples, understand how our sampling distribution is working, and it's helping us get around issues with like populations that are not perfectly normally distributed. So it's doing a lot of work for us. It's carrying a heavy load for us. Okay. So I'm gonna, let me see. Okay, I'm gonna go on to 2 here. Now, remember, we're getting a little ahead of lecture here because the lecture did everything we're talking about tonight except confidence intervals. Didn't talk about confidence intervals tonight. No reason that since we're here, we can't use it. Not to mention the fact that it's kind of a dead end to just calculate the standard errors over and over again. It's nice to be able to apply it a little bit. The other thing that came up is we discussed proportions. Okay, now, what is a proportion really? Well, a proportion is just basically a binomial variable. So, for instance, a proportion would be something like what percentage of people in this population have diabetes, right? So if you go sample a person, does the doctor tell you have diabetes? Oh, yeah. Somebody else? No. Yes, no, yes, no, yes, no. They either have it or they don't have it. So how do we express that? We express that as a proportion, right? We sample 100 people, 10 of them have diabetes. The proportion, the average proportion of people in that sample that have diabetes is 10%. So how do we express that here? Let me pack this away again, start again. I have to repeatedly open up this thing where I can write on because I updated my Mac OS, and of course the program I was using to do this Blackboard thing doesn't work anymore because it hasn't been updated for the operating system. And I don't have to tell you, it's update hell. So at any rate, that should be a lesson. So at any rate, proportions. Okay, so now let's say you have this population. This is all women in the United States between 40 and 60. That's our population, let's say, right? And it happens that the population proportion for diabetes within this population is, say, 8%, 0.808. Okay? We take a sample from that population. Say our sample size is 100, right? In a perfect world, we would wind up with our sample size is 100. We would wind up with 8 people that are diabetics and 80 and 92 people who are not diabetics. The perfect world, right? Okay, so how would I express that? I would say that P, probability of being diabetic, I'm going to use my sample to estimate my population. P is equal to 0.08, just like before. Except I need to distinguish between my proportion for my population and my proportion for my sample. I'm going to put a cap on here instead of a bar, like X bar, and I call it P cap. Whenever you see P cap, that's a proportion of a sample. Whenever you see P, I hate myself for saying this. Whenever you see P, it's the proportion of the population. That's true for these binomial variables. Later on, we're going to be using P to represent probabilities of error and stuff like that. Completely different use of P. But for now, let's work with just this version of P. Okay, so now, the problem I have is that I could have just as easily had 7 and 93 and thought P cap was equal to 0.07 instead, right? Because my population might be 8%. That doesn't guarantee if I take a sample of 100 people, I'm going to get exactly what the proportion is. However, I do know if I take random samples of 100 over and over and over and over again, then over time, I would expect my P cap to approximate my proportion to the population, right? If I took samples over and over and over and took an average of them. Well, what would I expect for the standard deviation, the spread of all of these samples? Well, we actually have a number that we can use to calculate the standard deviation for all the repeated samples of a certain sample size. And that's going to be equal to the, I'm going to call it standard error. That's going to be equal to the square root of P times 1 minus P over N, the sample size. Whole thing's under the square root. Okay, we saw that formula come up tonight, correct? What does that tell us? That tells us, now let's forget we know this. Yeah. Let's say, I guess I always use small n, but it doesn't matter. But let's say I don't know what the proportion of the population is, right? And I take a sample, and it turns out it tells me that the proportion of my sample is 8. 8 people out of 100 with diabetics. What can I do with this now? Well, first of all, I can say to myself, well, my first guess is 100 people, pretty good sample. I'm going to say that I think the population proportion of diabetics is about 8%, right? But gee, I don't understand. I don't know what my level of certainty for that is, right? So ideally, to use this calculator for standard error, I would ideally want to use P, the population proportion, right? If you're giving it in a problem, well, if you already know the population proportion, you're not going to go any further anyway. So for the purposes of proportion, I'm going to use my 8%. So what is my standard error going to be equal to for this proportion? My standard error is going to be equal to the square root of 0.08 times 1 minus 0.08, which is 0.92, over 100. Okay, let's figure out what that is. Okay, why don't I have a mouse? There it is. I have a mouse. It's not going anywhere. Oh, because that's leaning on there. Okay. Okay. Okay, you guys can do this along with me. Clear everything. So 0.08 times 0.92 is equal to this. I'm going to put that into memory. And actually, I don't even have to do that. I'm going to divide that by 100. And I get 0.000736. And now I'm going to take the square root of that number. And it comes out to be 0.027. 2.7% or 0.027. So what does that tell me? That tells me that if I were going to draw a distribution of repeated samples from this population, if I were right to begin with at 0.08, right, what I would expect to see is that the average for my repeated samples would be 0.08, and that the range, 2 standard deviations above and 2 standard deviations below, would be 2 standard errors below 0.08 and 2 standard errors above 0.08, right? Because this is my sample distribution, right? But I also now can calculate a confidence interval for my proportion. So how would I calculate that? I would say P cap plus or minus, I'm just going to do 95% confidence interval. What number I use for 95? 1.96 times the standard error, which is 0.027. Okay, so P cap is 0.08 plus or minus 1.96 times 0.027. Okay, let's find those two numbers. Okay, so I'm going to clear in my memory. That's 1.96 times 0.027. That's equal to about 5%. I'm going to put that in memory. I'm going to clear that. I'm going to say 0.08 minus, call that, it's going to be equal to 0.027. Clear. Then I'm going to add it, 0.08 plus, call memory, is equal to 13.92. So it's 0.02. It's roughly about 3% to about 13%. So it's 0.03 to about 13. So my sample came back 8%, but my level of certainty tells me that I'm 95% certain that the true proportion for the the average proportion for the population is somewhere between 3 and 13%. Right? Not great, but maybe a bigger sample would help me get. If I had a bigger sample, my standard error would have been smaller, right? Which would mean then that range would be smaller. At some point, we'll check my math there because it seems pretty wide anyway. So let's take a look at problem number 2. We want to know the true population proportion of Americans who are willing to accept the cut and living standards to help the environment. Lately, it seems like nobody. Right? Not a great year for the environment. In 2010, the General Social Survey asked a random sample of Americans how willing they were to accept the cut and living standards to help the environment. Out of 1,381 respondents, there's our N, 496 said that they were willing or very willing to very willing or fairly willing. What can we say about P? Well, let's start it. What's the sample proportion that would accept a cut and living standards? Anyone has a guess to answer to that part? How many people was it? Out of how many people?
36.
Whoops. Let me move this over so I can see them both. It was 13. It was 496. 496 out of 1,381. And what is that proportion? 35.99. Okay, 35.91. Okay, let's call it 35.9. 3.359. That's our proportion, right? Okay, that's our proportion from our sample. We don't know what our population proportion, everybody in the United States is. We only know what those 1,300 people responded. Okay, so what is the population proportion? Is the population proportion equal to the sample proportion? We don't know, right? No way for us to ever know. Calculate the standard error of the sample proportion. Okay, let's calculate the standard error for this. What's it going to be equal to? It's going to be equal to P times a P cap. In our case, I'm going to call it P because really we would love to use P from that, times 1 minus P over N and the square root of that whole thing. So what is that? That's 0.3. I'm going to call this 0.36 just because I don't want to be here all night. 0.36 times 0.64, right? 0.64 divided by, sample size was 1,381, and find the square root of this whole thing. Okay, get the calculator out. Actually, you guys do it first. Tell me what you get. Okay, any other opinions? Any other offerings from the peanut gallery? Anybody know what the peanut gallery is? What's the peanut gallery from? You guys are too young to know what the peanut gallery is, right? Huh? Howdy Doody. Right. Howdy Doody used to be this kids show that was on many years ago. They used to have a child audience, an audience of children. Like if you're really lucky and knew somebody rich or famous or something like that, you'd be able to get on the show. And while they were filming it, maybe about 30 kids or something like that. And they used to call them the peanut gallery. So at any rate, so let's see, 0.36. Let's see how right you are. Times 0.64, right? Divided by 1,381 is equal to that. Take the square root of that, and it's 0.013. Again, I'm rounding outrageously. Normally, I would tell you not to round until you were done with all your calculations. Equals to 0.013, 1.3%. Okay, so that is our standard error now. Okay, so now, what's the next question? Calculate the 95% confidence interval for the true population proportion. Okay, so what's that going to be equal to? That's going to be equal to P cap plus or minus 1.96 times our standard error, which is 0.013. Okay, and plus or minus. Okay, so what's it going to be equal to? It's going to be equal to 0.36 minus 1.96 times, well, it's going to be roughly 2 times that, which is roughly 2.6%. I'm going to call it 2.6%. Minus 0.026, right? And 0.36 plus that same value, 0.026. So if I add that to that, it's going to come out to 0.386, about 39%. Excuse me, 344 rather. And this is going to come out to 0.386. So what does that tell us? We're 95% certain the true population proportion for people in the United States that would accept a cut and living standard to protect the environment is between 34.4% and 38.6%. We're 95% sure it's not between those two numbers. What else do we know? What does that tell us? What can we deduce from that? We're 95% sure that a majority of the people in the United States will not accept the cut and living standard. Why is that? Because what proportion represents half of the United States? 50%. If we're 95% sure it's between these two numbers, and this number's over here, we know we're 95% sure it's different than that number. That's one of the ways we're going to be using this in the future, is to determine what level of certainty that this is different than some other proportion for some other group or some other test group or some other experimental group or for some outcome, say for an election, right? So for instance, let's see if we have some here. So for instance, I'm going to make one up on the fly. We're going to go back in time to November 2016. And I'm going to tell you that we did a survey, right, that said that 51% of the population said they're going to vote for Hillary Clinton, right? So our P cap is 51%. Our sample size is, let's say, 500. Okay, what's the probability that Hillary Clinton will get a majority of the votes? Okay. That's pretty, sample size 500 sounds like a big sample, right? Okay, 51%, not a big margin, but pretty big sample. What's our 95% confidence interval going to be? So you guys calculate that. Calculate the confidence interval for the proportion of the vote that Hillary Clinton will win. Okay, so my standard error is going to be 0.51 times 0.49 divided by 500, and I'm going to take square root. Square root is about 2%, 0.02. So I'm going to put this into my memory, clear it, and then I'm going to add and subtract 0.51 minus, recall memory, is going to be 0.487, 48.7. And the number, when I add it, is going to be 0.532.
But you didn't multiply by 196.
Yeah, I did, but I stored the number. Let me do it again. Clear? Clear. What I did was I put 0.49 times 0.51, right? Multiply those, divided by 500. right? Take square root of that. And then what I did was I put that into memory, right? And I cleared it. So now that's my margin of error. So I'm going to add and subtract that. I'm going to do it like you're going to use that to add and subtract for me. So I only have to do calculate this margin of error once. Once I've got it in my calculator, I don't have to calculate it again. So I took 0.51 and subtracted my margin of error, which is 0.02, and that's equal to that. And then I cleared that out, and I did the same thing. Yes? What happened there?
So what you get is the standard.
Hang on a second here. Let me make sure. Sharing main screen. How about now? I froze. That's odd. That hasn't happened to me for a long time. Let me stop screen sharing and start it again. Did it come back? It crashed on me. It's the first time that happened in ages. Show my screen. Main screen. So, yeah. I don't want. I said I was going to give you a break and get out a little early tonight. I killed that. Now we're up to the very end. But to make a long story short, okay, I calculated this number here, which was about what it was about 2.3 or something like that. 2.3. So I added that number to P, which was 0.5. I subtracted that number to P, which was 0.51. We got this. Then I added that number to P, and we got this. So I calculated this and then used it twice, once to add and once to subtract. You guys don't agree with me?
No, I'm totally confused. I don't know if I'm the only one. Can you go step by step?
Yeah, unfortunately, I'm frozen over there, so I can do it on the wall. Yeah.
So what did you do plus or minus? It's 0.043 plus or minus. Correct?
Okay. I calculated the standard error. The standard error was equal to 0.51 times 0.49.
Divided by 500.
And take the square root. And that came out
0.022.
0.022.
Correct.
So I took 0.022 and put it in here.
Right.
And I multiplied by 1.96.
And you should get 0.043.
Oh, maybe I made a mistake. You guys are right. I probably made a mistake. You're right.
And then it's plus or minus 0.043 to 0.51,
Right.
which is 0.467.
So this should be 467, and this should be 553. 553. Okay, so you guys had it right.
Okay.
You're right. I forgot to multiply by 1.96 before I put it in memory. Okay. So now what does that tell you? What does that tell you? That sample of 500 people might have been 51% in favor of Hillary Clinton, but in the general, if that's a true random sample, the general population, you're 95% certain it's between 46 and 54%. So it's far from a certainty about that population, right? So if this were a poll, they would call this number the margin of error. And you want to know something, stay sneaky that they do, is that, if Donald Trump has 35% in a poll, and Mitt Romney has 25%, and Ted Cruz has 12%. Well, then you notice that your standard errors for each one of those guys would be different, right? So you'd have a different margin of error for each. So they juggle the numbers a little bit. Instead of using the p-value for each individual person in that poll, they use 0.5. So instead of using 0.12 for Ted Cruz, they use 0.5. So it's 0.5 times 0.5 over the sample size, right? Or 0.5 times 0.5 for Donald Trump over the sample size. So all the margins of errors come out looking the same, right? So that's why sometimes you see a poll like that and you say, oh, look, this proportion is this proportion is this proportion is this. It's one sample size. How do they get the same margin of error? That's how they get the same margin of error. And it's actually legitimate to do that because 0.5 times 0.5 will give you the biggest number for the standard error. If you play around with the numbers and you go home, if P is equal to 0.5 and you have to do 0.5 times 0.5 over N, then that number will never be bigger than any other proportion. 0.4 times 0.6 will be smaller. 0.2 times 0.8 will be smaller. So it's kind of legitimate to do that because if anything, you're exaggerating the margin of error, not making it small. But that's only for you guys that are interested in polls and stuff like that. Good enough. Okay, guys? All right, that was interesting though, right? So now this is cool. We're getting into real statistics here. This is something now that we can take and we can start. And you want to know something? Just go online and like Google a few studies and stuff like that, like abstracts, lead studies, abstracts or something like that. And I'll bet that when you look at a lot of those abstracts, a lot of them will say, well, we did a study with children in the Bronx in lower income housing, and the average blood lead level was 5 micrograms per deciliter with a 95% confidence interval. It'll put in parentheses next to that number, they'll put the confidence interval that they calculated. Right? So you'll always see that anytime you see an average from a sample poll. Okay, and don't rat me out. Don't rat me out to Professor White and say I went ahead of the lecture. Yes.
Yeah, we're just gonna work on it.
Oh, further?